This presentation was originally designed for the astronomy group, but hopefully it should be applicable to both astronomy and the geology group. By way of introduction, geology is the science of describing the Earth's forms and materials. It's used to infer the processes and reactions that gave rise to these. But you have to ask, do geological facts apply on other planets and moons? Let's explore some accepted facts and take them into outer space. All planetary geology in the solar system had a common beginning. This video hopefully should explain that.
Our solar system is the region of space which falls within the gravitational influence of our sun. The solar system is thought to have begun forming about 5 billion years ago from a giant spinning cloud of gas and dust. The core of this cloud grew under the influence of gravity and became denser and hotter. As material fell towards the growing core, the cloud increased in speed and flattened into a giant spinning disk. Eventually, the increasing temperature generated enough energy to trigger nuclear fusion. This fusion marked the birth of our sun. The lighter gas was swept far out into the solar system, leaving heavier, rockier material and metallics with high melting points nearer the sun. Molten metal and dust particles stuck together to form clusters, which in turn stuck together to form rocks. Mutual gravity caused these rocks to come together, eventually to form planets. In the hot inner regions of the solar system, rocky planets with metal cores were formed. In the colder outer regions, things were different. Further from the sun, temperatures dropped. Water vapor condensed and turned to ice. This ice, combined with the vast amounts of gas blown away from the sun, meant there was a lot more material here than in the inner regions. As huge cores of ice and metal grew, the gases swept away at the sun's birth were attracted through gravity. When the accretion of most of the ice and gas was complete, we were left with the gas giants. The solar system as we know it is around 4.6 billion years old.
So, given that all planets and material in the solar system have a common origin, on the Earth we describe rocks as being of three types: igneous, sedimentary, metamorphic. So you have to then ask, do these terms have any meaning off the Earth? The process of the main rock types on Earth, you have volcanic eruptions. You then find that the lava cools and becomes igneous in nature. Lava that's intruded into the Earth is similarly igneous. That lava will be ground down, weathered down into fragments which form sediment. Sediment itself is transported often by water, sometimes by air, and accumulates. As it is gradually buried by further sediment, it forms sedimentary rock. Sedimentary rock in turn gets further buried and under heat and pressure gets metamorphosed into metamorphic rock, similar to the sort of stuff you would see like chalk becoming marble. Metamorphic rock in its turn will be further buried and under more heat and pressure will liquefy back into the magma that it originated from. As that gets buried, that magma will eventually escape through a vertical pipe to form an eruption on the surface, and hence we return to volcanoes where we started from. So let's look and see if these processes apply to the moon, our nearest neighbour. Is there a rock cycle there? Let's look at how it was formed as distinct from the Earth. The Earth has a high density generally and has a large molten iron core. The moon has a lower density than the Earth, and it has an iron core, but it's very much smaller, even in proportion to the moon's smaller size. The hypothesis that tries to explain that is the giant impact hypothesis, and this video will try to explain how that originated. Early Earth was struck by a Mars-sized object known as Theia. The small object is Theia, about the size of Mars. It hits the Earth and instantly the crust is liquefied. It shares crust with the Theia object. Most of the iron core from Theia is transmitted in to the higher gravity of Earth and becomes part of Earth's core, which would explain why the moon has less of an iron core. Of course, the moon is then orbiting as an amalgam of crust from the Earth, crust from Theia, and it's in a debris field orbiting the newly deformed Earth. That debris field will of course form the basis of a further bombardment, as it in turn is attracted either to the Earth or to the newly formed moon. Once the moon had formed, the following is a likely scenario. The moon of course is molten to begin with. As it cools, some of the larger pieces of debris that are in orbit around the Earth collide, both with it and the Earth. The heavy bombardment is of course the larger fragments, and those larger fragments cause the plains to become molten. Those molten plains are what we know as the mares, or the seas on the moon. They're actually lava plains that are now solidified. Similar, the Sea of Tranquility is one such. The smaller pieces of debris rain down over the moon and the Earth in the succeeding millions of years. And you see the moon as it is today. So given what we know about the moon, you then have to look at how we know that there were several periods of bombardment. Craters in the moon typically are aged by a process of two distinct methodologies. You look at the overlapping order. So in the illustration here, you would see that D is the oldest crater, A is the next oldest because it overlaps D, C would be younger than A because it overlaps A, and B is the youngest because it overlaps C. You also have the amount of cratering within a crater, because of course once it forms, it would continue to be being bombarded. And so if it's got less craters within it, then it tends to be a newer crater. There is no weather as such on the moon because of course there is no atmosphere on the moon. Moon rocks were all molten, so by definition they're igneous. Since there's no volcanism and there's no magnetic field, because it's such a small iron core and it doesn't generate enough magnetism by virtue of the dynamo effect. You've got low gravity and no atmosphere, so therefore any gases that are vented off by the volcanism of the moon's creation get stripped away by charged particles from the solar radiation. So you have to ask yourself, in the absence of weather, how do rocks erode to dust? And clearly there is dust. We all are familiar with the footprints from Armstrong and Aldrin, and it is a thick layer of dust. Meteorites and micrometeorites rained down on the moon for billions of years and would smash pieces of rock into successively smaller and smaller fragments. Now, solar radiation would then act upon those micro granules and further cause changes within the chemical structure. But these rocks are blasted down into microscopic shards. Much of it is molten glass shards because of the heat of their creation. And there is no weathering or water to round off these shards, so they are as sharp as the day they were formed. When we went to the moon, we found the dust was as fine as talcum powder, and in fact some of it was as fine as cigarette smoke, but it was as abrasive as emery paper. It floats in low gravity, it's attracted by static electricity to stick to surfaces. It enters seals, joints, bearings, human eyes and lungs. These are some of the comments of the astronauts who landed on the moon. So, another fact that we accept, in the last 75 years, it's been accepted that plate tectonics on Earth is the basis of all geology. You'll be familiar that Venus is the planet that is next closest to the Sun from us. It's roughly the same size as us, slightly smaller. It has a very slow rotation, 243 days. So that means that its day is almost as long as its year. Now, it has no magnetic field. Well, why is that? The fact that it's rotating so slowly may mean that presumably it's got an iron metallic core like we have, but because it isn't turning, it isn't generating that dynamo magnetic field effect that the Earth fortunately has. The effect of that is that charged particles from the Sun typically strip away oxygen and hydrogen from the upper reaches of the Venusian atmosphere. So that leaves an atmosphere that's mostly carbon dioxide with thick sulfur dioxide clouds, which are very reflective, which is why Venus is so bright in the evening sky. What you have is a runaway greenhouse effect, because on Earth, the oceans absorb most of the carbon dioxide, and it is converted both by chemical processes, but also by life. It is converted into limestones. And so it's trapped because it then gets buried. So that takes the carbon dioxide out of circulation. Of course, because Venus has lost its oxygen and hydrogen, it has boiled away its seas, if it ever had them. And so, of course, there is no sink for those greenhouse gases to go into. So what happens is that you have incoming sunlight. That sunlight is mostly reflected away, but some gets through, and of course that warms the planet. However, the radiation of a warmed planet is infrared. That is absorbed by the greenhouse gases, and so cannot escape to the same extent. So you get a very small amount of radiation of heat back into space. Effectively, you've got a pressure cooker here, and that greenhouse effect becomes a runaway greenhouse effect. A radar image of Venus shows that it's got a surface temperature that's the equivalent of a pizza oven, 470 degrees. You have a pressure that's the equivalent of being a kilometre under sea. It has large, sparse, low-shield volcanoes. Its surface is largely flat. Very few craters, which would indicate that it's a young surface. So you ask, well, how can that be for a planet almost the same size as the Earth, almost in the same position vis-a-vis the distance from the sun? The fact that it's slightly closer doesn't explain its enormous temperatures, because of course this is the hottest planet in the solar system, much hotter than Mercury, which is much closer to the sun. So it is the greenhouse effect that is the predominant feature here. If you look at Earth, the tectonic model that's been accepted is that you have a cool atmosphere on Earth, 4 degrees is the average, which tends to mean that the crust is thick. It cools by radiating off heat, and so it becomes thick. By virtue of the fact that it's thick, it's also brittle and cold, so it cracks, and it cracks vertically. Those vertical cracks are where the planet releases its heat. And if you look, you see typically the ring of fire that is so famous, extending up from New Zealand to Japan with volcanic eruptions and earthquakes. You have the Mid-Atlantic Ridge, which is, of course, where you find smokers, black smokers, white smokers. You have hotspots such as Hawaii, in the Pacific, where you've got mantle plumes radiating heat through volcanic eruptions. And you've got subduction zones such as the Andes, where you've got volcanoes again as a result of cracks where one plate is subducting underneath another. Let's look at the model for Venus. Venus has got a much higher surface temperature, 470 degrees, as is the atmosphere. So therefore, the crust doesn't cool, which means that it's thin. The lithosphere, which is the underlying layer of the crust, remains fluid and ductile. As a result, it's difficult for the planet to lose heat. What tends to happen is that mantle, which has melted, tries to bubble up. Of course, the ductile lithosphere moves aside, and so it becomes horizontal sills, which is magma chambers. The BDT is the brittle ductile transition zone. Effectively, that's, if you were thinking of this as a creme brulee, this would be the hard part of the creme brulee, and this would be the part which is relatively creamy. So the creme brulee part in Venus is actually very thin. What then happens is that the cells merge and expand laterally. Eventually, they cause the thin crust to upwell and fracture. The magma intrudes into the dikes and ponds. As you see here, you end up with a pancake dome, which is a corona. And of course, with any volcanic eruption, you get sulfur dioxide and carbon dioxide gassed out. This is a typical corona, a low shield volcano that you see on Venus. And there is no pattern to them, unlike on Earth, where you can actually see the plate boundaries. These are randomly interspersed across the surface. So, given that you've got this gassing, outgassing occurring, of course, what happens? You've got a weakened lithosphere. You've got an increase in greenhouse gases, which drives up the air temperature in Venus, which further thins the lithosphere and the crust. Eventually, over time, the crust becomes so thin that you get complete crustal failure, and you have lava which resurfaces the entire planet. Now, we've had similar things in the past on Earth. The Deccan traps are one example, the Siberian traps, where you've had vast lava plains. But of course, we've never got to the greenhouse, the runaway greenhouse effect that we have in Venus, because the oceans have been able to absorb much of the excess greenhouse gas, and life has too. Another accepted geology fact. Geology is the interaction of rocks, energy, water. Now, you'd expect to find that closest to the sun, where the energy is. The inner hot rocky planets are where you'd find active geological processes, because that's also where liquid water and its interaction with rocks will be found. Apparently that's not what happens, and this is something that we've recently discovered. The outer gas giants comprise of Jupiter, Saturn, Uranus and Neptune. They're mostly composed of gas, although under very high pressure and quite exotic in their nature. They're formed from the majority of the solar nebula that didn't form the sun. Because they've got a lot of mass, they've got a high gravitational pull. And this gives you an example of the sort of comparative sizes of the sun and the planets. You can see that we are in the minor league here, and Jupiter and Saturn compose the vast majority of gases outside the sun. Uranus and Neptune bring up the remainder. Now, each of these have hundreds of moons, many captured, in much the same way that debris will eventually be attracted by gravity towards the larger gas giants. They go into orbit around them, they collide, they accrete. But some, Titan and Ganymede, are much bigger than than Mercury, our innermost planet. Voyager and the other probes showed two types. There were the rocky types, typically that's Io, one of the moons in Jupiter, and you have the ice moons. So let's look at Io first. It's the innermost of Jupiter's moons. It's the only major moon, other than our own, that's mostly rocky. It's a kaleidoscope of colours. And this video explains where these colours come from.
Extreme pressure and sub-zero temperatures aside, there are volcanoes and lava lakes dotted all over its uneven rocky terrain. The surface is constantly being reshaped by this volcanism, and Io has over 100 mountains which have been uplifted by compression at the base of Io's silica crust. Some of these mountains are taller than Everest. Of course, mountains are one thing, but what really sets Io apart from the rest of the solar system's moons are its 400 active volcanoes, making it one of only a handful of active moons in the solar system, and by far the most violent and extreme. Volcanoes on Io erupt lava rich in sulfur and magnesium dozens of kilometers into the air, and plumes of sulfur and sulfur dioxide as high as 500 kilometers. These volcanic depressions are connected and joined by massive lakes of silicate lava. The largest is Loki Patera, which is over 200 kilometers across, 1 million times larger than any lake we have on Earth, and single-handedly responsible for 25% of all of the heat emitted by the moon. With erupting mountains and vast lava flows, Io is truly a sight to behold. But why is it that this moon is so volatile and volcanic, and none of the others that we know of are?
Well, let's explore that. Why is Io so volcanic? Io's orbit gets tugged from a circular orbit into an ellipse by the other orbiting moons of Jupiter, When it's closest to Jupiter, it's stretched by Jupiter's gravitational field like a rugby ball. And this gives you some idea of the effect. Of course, here at the closest point, it's elliptical and it becomes more spherical the further away it gets in its orbit. Its surface shifts by approximately 100 meters each orbit, and the friction from that generates enormous amounts of heat. And that's the tidal heating that is the source of the magnetism on Io. Now let's look at the ice moons. Many ice moons show chaotic linear structures and near absence of craters. And of course, that later fact would indicate that these are young surfaces. Europa, Ganymede, Enceladus. You can see these features and the relative lack of cratering, particularly on Enceladus and Europa. Now, if you look more closely, you can see the sort of features that are typical of these icy moons. You've got features that look like the sea, the frozen Arctic in the spring. You've got pressure ridges, you've got faults, you've got blocks that have clearly moved and rotated, you've got linear upwellings. This is a moving surface, it's undergoing renewal. Now, what mechanism would be driving that? Some, like Saturn's Enceladus, have been found to have geysers erupting water 200 kilometers into space from these cracks between blocks. That would indicate there's an ocean underneath these. And an ocean, a liquid ocean, would have to have a heating source, and tidal heating would be the most likely candidate.
The instrument acts like a human nose, analyzing the smell, so to speak, or the composition of the gases in the environment. There was a significant amount of molecular hydrogen. The existence of molecular hydrogen, at least within the Earth's ocean system, is like a food source. It's candy for microbes. They eat the hydrogen, they turn it into methane. And with our findings, we were able to not only find out that there was H2 in the system, but to examine the chemistry that's associated with that process of taking hydrogen and turning it into methane. Here on Earth, the hydrothermal systems known as white smokers have water-rock interactions that lead to the release of molecular hydrogen in a similar fashion to apparently what's going on at Enceladus. This is just the final step that shows that there's molecular hydrogen being produced by these same hydrothermal processes, and that molecular hydrogen has the chemical energy to support microbial systems in the interior ocean. It's not demonstration of binding life, but it shows the potential for the existence of life in this interior ocean.
So you can see from that that these ice moons are really ocean moons with an inner heating source. And the following icy bodies have global oceans under icy crusts: Callisto, Ganymede and Europa, which orbit Jupiter; Titan, Enceladus and Mimas, which orbit Saturn; Neptune's moon Triton; and interestingly, the dwarf planet Pluto, although its heat source is different insofar as it's more likely to have been as a result of an impact with another body. Now, the surface of these moons gets even more exotic. These are deeply cold environments on the surface. and the Cassini probe to Saturn photographed Saturn's largest moon, Titan. What it saw was water ice that made up landforms, mountains. These are as hard as granite at these temperatures, and so water ice becomes the landforms. Lakes and rivers of liquid methane were seen, and this is what you would burn on a gas cooker. It's natural gas, but it's in liquid form, it's so cold. Sunlight is shown reflected of these methane lakes. Cassini carried a lander, Huygens, and this shows you what happened as Huygens descended towards Titan.
January 14th, 2005 begins with the Earth passing directly in between the Sun and Saturn, an opposition so perfect that it occurs maybe twice per millennium. Meanwhile, the Huygens probe, quietly entering the Saturnian system, is about to end its 7-year journey. As Huygens approaches, the inner planets cluster around the distant Sun. Saturn appears almost as large as Orion. A few moons are visible as white dots aligned with Saturn's rings, while Titan, its largest moon, is already well resolved. Huygens is destined for Titan, a mysterious world larger than the planet Mercury and shrouded by a thick brownish-orange atmosphere. The details of its surface have never been seen. Huygens' speed increases to near 6 kilometers per second, and Titan's disk quickly obscures our view of Saturn and its more intimate moons. As the probe enters Titan's atmosphere, the heat shield reduces the speed some 15-fold within a few minutes. The main parachute reduces the speed further. 15 minutes later, the smaller stabilizer chute allows a faster descent at first, but slows as Huygens enters the lower, denser part of Titan's atmosphere. Huygens is approaching a dark valley between brighter, hilly regions. Beyond the hills to the left, 2 dark parallel lines appear, which are later discovered to be part of a vast system of dunes which surround the moon. At 21 kilometers altitude, the probe moves through a thin haze layer as seen on the horizon. The bright area near the center top is the glow of Titan's haze illuminated by the sun. A complicated system of drainage channels, some hundreds of meters wide and kilometers long, are seen cut into the hillside. These are probably the result of runoff from methane rain. Stereographic imagery reveals hills to the left to be perhaps a few hundred meters tall, while features in the valley are tens of meters in height. For most of the descent, the probe travels eastward above Titan's surface. However, below 7 kilometers altitude, the motion reverses into a backward westward motion. It reverses again at 1 kilometer altitude, and we move slowly southeastward. Hang on as Huygens lands on Titan's surface near a water ice outcropping ridge. Another westward-looking view of the descent from 31 kilometers shows the area of Titan over which the probe has just flown. This affords us a good view of the drainage channels and apparent shoreline. More dark lowlands appear and a rough pitted hillside to the left. Spectra of the surface suggest that the bright areas are water ice, and the darker areas are a type of hydrocarbon mixture that has never been produced in the laboratory. The small white dot in the lower center part of scene tracks our progress over Titan's surface. We see the reversal in direction at 7 kilometers altitude, and we fly over the ridge near where we will land. As we approach the surface, our perspective brings the topography to life. We see that although there are rivers and a shoreline, the basin is dry. Below, there are distinct signs of erosion which crafted the rugged ridgeline. Huygens sinks into one of these gullies. We experience a relatively soft landing on Titan's surface. The view from the surface reveals an amazingly Earth-like picture of a dry riverbed with distant hills which are a few meters in height. Some seconds after impact, the shadow of Huygens' parachute drifts across the scene. The heat from the surface science lamp in the probe's skin vaporizes methane from Titan's surface, which is about 180 centigrade degrees below freezing. Near the probe, the ground is littered with water ice rocks and smaller pebbles which could be made of water ice, or hydrocarbons, or some combination thereof. Although we now know more than ever about this mysterious world, many questions remain unanswered. Where is the vast reservoir of liquid methane necessary to replenish the atmosphere? Where and how often does it rain on Titan? How does the methane get recirculated into the atmosphere? What materials make up the surface? What processes create and shape the hills, dunes, and valleys?
As you can see, in such a cold surface, you get some fairly exotic surface geology. There's a dense hydrocarbon smog. The nitrogen atmosphere with methane and ethane clouds leads to methane rain, methane rivers and lakes. Titan's methane cycle is analogous to Earth's water cycle. Water ammonia ice on Titan is the landform that is composed of rocks on Earth, and so that's the equivalent. It forms mountains, dunes, and rocks. Cryovolcanoes erupt hydrocarbon slush like lava. So you have some similarities, but some exotic dissimilarities. Go further out, for example, to Pluto. It's even colder, 240 degrees below zero. Nitrogen is solid on Pluto. And it's thought that Pluto has a subsurface water ocean.
Upon arrival at Pluto, the images are astonishing. Data gathered from New Horizons showed that Pluto and its surrounding natural satellites were much more complicated than anyone here on Earth could have possibly imagined. In particular, scientists were amazed by the degree of activity that could be found occurring on the surface of the planet. Take, for instance, Sputnik Planitia. Named after the first artificial satellite sent out from Earth, this is a heart-shaped nitrogen glacier and is thought to be the biggest glacier found anywhere in our solar system. Strangely enough, this massive glacier may be a relatively new feature of Pluto's topography. New Horizons was unable to detect any crater marks on the glacier's surface, which implies it was somehow formed within the last 10 million years. Scientists believe that Sputnik Planitia was actually formed as the result of a massive impactor slamming into Pluto's surface, one that would have been between 150 kilometers to 300 kilometers wide. The resultant basin would have collected up the nitrogen ice in the area, forming the massive glacier we know today. Pluto's nitrogen ice glaciers have another interesting quirk that hasn't been seen anywhere else in the solar system: massive hills of water ice floating atop the nitrogen ice. These isolated hills can be anywhere from 1 to several miles across, as reported by New Horizons data. Because water ice is less dense than nitrogen ice, it is thought that the hills float across the surface of Sputnik Planitia, incredibly similar to how icebergs would float across water on Earth. It is most likely that these nomadic hills are chunks of ice broken free from the rugged uplands of Pluto, drifting through the convections of the nitrogen ice of Sputnik Planitia. New Horizons was also able to uncover Pluto's strangely bladed surface structures. These massive blades stumped scientists when New Horizons first observed them in 2015, but over the years they believe they have found an answer. Scientists believe that these blades are actually giant spires of methane ice, some as tall as a skyscraper in New York. Scientists believe they have been caused by sublimation, a process caused by climatic variation on the surface of Pluto. When it is slightly warmer, the methane ice begins to simply evaporate into gas, skipping the liquid form. This creates the gigantic features known as penitents that we see on the surface. A similar effect can be seen in high-altitude snowfields on Earth, but nowhere near as large as the blades of Pluto.
So you can see that the sort of glacier in Sputnik Planitia here, you can see that there's movement into a basin here. The glacier then flows further out of the basin onto the low-lying plain around it, using channels, just as glaciers do on Earth. There are cryovolcanoes, similar to volcanoes on Earth, which erupt, not lava, but a hydrocarbon slush. You've got dunes. These are hydrocarbon particles which are blown by differences in pressure, where you've got a part of Pluto that's exposed to the sun, the pressure is obviously higher than the area that's shaded, which is at low pressure, and so you get movement of the thin atmosphere combined with the low gravity of Pluto drives these particles. And you've got polygonal ice cells here. And this is similar to your teacup, where the center of the teacup is hot, the outer rim of the teacup is cool. And so you have a plume of warmer water coming up underneath. It drives the center up, but of course the outside, which is cooler, remains depressed. So in summary, geology is a toolbox, but it's obviously one with new tools. Geo means earth. Astrogeology introduces several new concepts. You have impact geology, cratering, lava lakes or mares on the moon, for example. You have tectonic alternatives, such as the global resurfacing we saw in Venus. You have low gravity geological formations, such as the Penates on Pluto. You have tidal heating and subsurface planetary oceans, such as we saw on Titan and Enceladus. And you have cryogeology, exotic ice formations, composed of various elements in their gaseous or solid forms. Ultimately, geology may even be getting back to its roots. NASA has a competition: mining. Thank you for listening.